Hey, welcome back to Calculus. In this video lecture, we're going to start our work in Chapter 3 by taking a look at some differentiation rules. And in particular, in this first section, we're going to learn how to differentiate any polynomial function. All right, so you're looking at the objectives there. I'll just kind of walk through them with you as we get going. First, I just kind of want to remind you of something we've already talked about, that the derivative of a constant function is zero. Functions that don't change have zero rates of change. And then I want to show you some differentiation rules. These things are going to facilitate being able to compute derivatives much quicker. In particular, the main one of this lecture I want to tell you is something called the power rule. And then there's some, and then it applies specifically to a certain kind of function called a power function. I'll tell you what one is. And then there are three other more general rules, how to deal with when you have a constant multiple of a function, the sum of two functions, and the difference of two functions. Okay, so we're going to look at those three differentiation rules, and then together with those four things, the power rule, constant multiple, sum, and difference rules, we will be able to differentiate any polynomial function. All right, so that's our goal. Let's get going here. I want to start by just kind of reminding you of that fact that if you take a constant function, its derivative is zero. We can do that analytically, algebraically, we can calculate that, but it's also important to hold on to the geometry here. If you take a constant function, let me just sketch a quick graph as we're talking here. So what's a constant function look like? Well, it has some value. I'm going to call that value C. Let me actually move my label a little bit. It's a number on the y-axis. And the outputs, no matter what x is, the outputs of the function are C. So if you just write it as an equation, y equals, it's y equals C is a horizontal line. And that horizontal line has slope 0. Yeah, at every point, the slope is 0 on that line. So that's one way to see why this is true. The derivative of a constant function is 0 because the slopes are always 0. If you want to do it algebraically, the derivative, I'm just going to write, of this constant function by the limit definition of derivative, we would take the limit as h goes to 0 of the function's value at x plus h. Well, that's c. This function only has one value. And then subtract the function's value at x, I get c again. And c minus c is 0. And if you take the limit as h goes to 0 of 0 over h, you're going to get 0. All right, so that's our first objective. The derivative of any constant function always has derivative 0. Not a difficult, but yet very important fact. All right, so now let's move on to power functions. I want to start by telling you what I mean by a power function. I'm going to reveal this a little bit slowly because I've got a busy slide below it. But by a power function, I mean a function of the following form. You're looking at one here. Let me just highlight it so I know you're looking at the right place. It's a function whose variable is the base. So you're raising powers. And then the exponent is some, and we're going to start by saying it's some positive whole number. So a number like n equals 1, 2 by an integer, if you're not familiar with that terminology, I mean a whole number. A whole number greater than or equal to 1 is a positive integer. And then for this power function, that's fixed. So you choose an n, it doesn't change. The variable is the base down here. So you're used to functions like this, like, let me just try to make a little bit more room. Functions like x to the 1, x squared, x cubed, x to the 4th. Maybe you called them monomials or something when you were studying polynomials. These are what I mean by power functions. And I want to take the derivative of them. And so using the definition of derivative, we're going to have to be looking at a quantity x plus h raised to this power n. So that's now I'm going to reveal on my secret slide here. I've written out some of the computations of when you take something like x plus h to the first power or x plus h to the second power and so on. Yeah, you can expand these things with something called the binomial theorem. Maybe you know Pascal's triangle or something like that, but you can also just multiply it out and gather like terms. So if you like, that's kind of what I've done. And I just wanted to arrange them here. I mean, I think some of these are very familiar, right? X plus 1 to the h, x plus h to the 1. There is no multiplication to do. X plus h squared, you can expand out with that familiar FOIL pattern and so on. Maybe if you know Pascal's triangle, you know why these coefficients are 1, 3, 3, 1 for the 4th power, 1, 4, 6, 4, 1. There's certainly a beautiful pattern in there. But I've just expanded all of these things out, okay? And now I'm just kind of looking at a pattern. And here's the pattern that I know. I think I'm going to start with maybe x plus h cubed. I'm looking at this line. So I noticed that it starts off x cubed. In fact, all of these things do. When you're taking x plus h to some number, the first term is always x to that number. And then in the second term, in each one of these things, you end up getting that number, n times x to the power that's been reduced by 1 times h to the first power. Yeah. So when n is 4, you get 4x cubed h. When n is 3, you get 3x squared h. So down here in my kind of general thing, it starts off x to the n, and then my first term is going to be, second term, sorry, n times x to the 1 less than that, n minus 1 times h. And then the rest of this stuff, I just want to remark, has terms that have at least h squared in them, at least a factor of h squared. Like, look, here's an h squared, here's an h squared, h cubed has got a factor of h squared in it. There's an h squared, an h cubed, an h to the fourth. So that pattern will continue. And I'm just going to write that kind of generally like this, terms with factors of h squared in them. Okay, so this comes from the binomial theorem. So how are we going to use that to take our derivative? Let's see if I've given myself enough room to write this computation. I'm going to squeeze off the top a little bit there, but I'm interested in taking the derivative, d by dx, of this power function, x to the n. So our limit definition of the derivative says we should take the limit as h approaches 0 of, you got to plug in x plus h. So x plus h needs to get raised to the n. That's why we were looking at those expansions above. I've got an expression for it right up there. And then you need to subtract off the value at x, that's x to the n, and then divide all of that by h. Okay, so I'm going to slide down. I've got it written, but basically I'm going to replace this x plus h to the n with this version of it. Yeah, x plus h to the n is x to the n plus n times x to the n minus 1 times h, plus a bunch of stuff that have at least h squareds in them. Okay, so if I scroll down a little bit, you can see that next part of the computation. What have I done? I've just replaced my x plus h to the n with that expression that we worked out with the binomial theorem above. I still have to subtract x to the n from that, and then divide the whole thing by h. All right, but now we can kind of start seeing some of the usual cancellations that we see. This x to the n shows up once with a plus sign and once with a minus sign, right? And then once those terms are gone, those are the only two terms with no h's in them. Yeah, this term has exactly one h. These terms all have at least two. Yeah, so you can factor h out of that whole expression and cancel this thing, so we can use our direct substitution principle. I'm going to kind of just do this a little bit lazy, switching color a little bit, but this h will cancel that one. It'll be gone. And then in these terms, since they all have a factor of h that's at least 2, there's something in there that can cancel that h. Yeah, so if I scroll down a little bit, this is what would be left. I'd be left with my first term, but the h is gone because it canceled. And then in the rest of these terms, I would have at least a factor of h to the 1, yeah, because they all used to have at least 2 h's, but we canceled one of them. So there's at least one left. Okay, well, when you let h go to 0, there's no h's here at all, so that term's just going to stick around. Anything with an h in it, once you let h equals 0, is going to be gone, because anything times 0 is 0. So at the end of the computation, here's what we get. The derivative just simplified down to n times x to the n minus 1, all right? So that's the derivative of the power function x to the n. So let me reveal this box, and I clipped it from your text, and we're going to call this the power rule. All right, so what's the author saying? He's saying that if n is a positive integer, remember what that means. It just means that n is a whole number that's greater than or equal to 0, so excuse me, greater than 0. So n is a number like 1, 2, 3, and so on. Then the derivative of x to the n is n times x to the n minus 1. So you kind of can memorize that formula by saying, okay, you take your old exponent, the n, and you make it a coefficient, and then you write x to the number that's 1 less than that, right? We've seen some examples of this before. When we differentiated x squared, maybe I'll just write it right here in this box. So for example, the derivative of x squared Yeah, our squaring function, we computed it by limit definition before in chapter 2. If we were going to use this power rule, okay, well, my exponent is 2, so that 2 becomes a coefficient, and then I write it times x to the number that's 1 less than 2, and the number that's 1 less than 2 is 1. So here's how the power rule quickly produces that result, that the derivative of x squared is 2x. Okay, let's look at some other examples. I've got a whole bunch of them here. Let me just reveal several of them at a time. I'm going to try to keep that power rule visible. In these examples, I'm kind of, well, I want to illustrate the power rule and also illustrate that it doesn't matter what the name of the variable is, and we have different notations for the derivative. So I'm just trying to get you used to all of these notational ideas. So let's just look at these things one at a time. How about if we want to take the derivative of the 7th power of x? Okay, well, the power rule says that you bring that 7 down, and you multiply it by x to the power that's 1 less than 7. So it's 7 times x to the 6th. Yeah, so that's just a consequence of this rule that we just derived. Doesn't matter what the power is. Here I've got x to the 101, our Humboldt County highway number. I'm writing it in not function notation, but writing y equals x to the 101. Okay, so y prime, it means the derivative. You bring that 101 down, and you multiply it by x to the number that's 1 less than 101. That's 100. The power rule greatly simplifies these computations. Here, no big deal. I'm using Leibniz notation in the third example, and the input variable is called z. So I'm differentiating z to the 17th with respect to z. Okay, so the power rule says that that derivative would be 17 times z to the 16th, right? So this is kind of one nice thing about the Leibniz notation, is that it's built in what you're taking the derivative with respect to, because that's asking the question, what is the rate of change with respect to? So this is kind of, maybe I'll write this in cautionary red, but maybe here's a good thing for you to think about. If somebody wrote, what's d by dx of z to the 17th? So I'm asking, well, how does z to the 17th change with respect to x? Well, there's no x's in here. Yeah, z to the 17th. This is a subtle concept. I think I would stop the video after I say this and think about it for a second. Ask me about it in an office hour. Z to the 17th is constant with respect to x. Yeah, this thing does not depend on x. It's a constant with respect to x. So if you take its derivative with respect to x, well, the derivative of a constant is 0. Yeah. So that's a subtle thing, but make sure that you can kind of stop and understand that the derivative of z to the 17th with respect to z is 17 times z to the 16th. But with respect to anything other than z, the derivative is going to be 0, because z to the 17th only depends on z. Cool. How about this last example? What power of x is x itself? Well, it's x to the 1. Yeah, so the power rule says, well, bring that 1 down and multiply it by x to the number that's 1 less than that, 0. But x to the 0 itself is 1. So the derivative of x is just 1. An important fact. I think I want to even emphasize it by writing it kind of nicer. If you take the derivative, I'm going to switch back to the Newtonian notation of x itself, you get 1. Cool. All right. I'm not going to prove this. I'm just going to state it without proof, but the power rule actually works for any exponent. It doesn't have to be a positive integer. If you take any real number exponent, yeah, so in particular, it can be fractions, it can be numbers like pi, any real number exponent. If you're differentiating x to the n, then it's always true that the derivative is n times x to the n minus 1. So your author's calling this the general version of the power rule. So we only gave a proof for it, kind of using the binomial theorem above for positive integer values of n, but in fact, it's true for any real number. So what does that mean? Let's look at some examples. I think I want to kind of reveal these one at a time. So here, maybe I want to take the derivative of the square root of x. The square root of x doesn't look like a power function, but it is. Yeah, maybe you remember from your pre-calculus class that radical functions like this, the square root of x, can be written as an exponent. You know what exponent the square root of x is? It's the 1/2 power. The square root is the 1/2 power. And for differentiation purposes, you're going to hear me say this a lot. For differentiation purposes, I'll always treat the square root of x like a power function. So I can use this power rule. All right. So using the power rule, what do? We take the exponent, bring it down, and then we have to multiply that by x to the number that's one less than that. So I can write that, that's the new exponent, 1/2 minus 1. And then just by doing a little fraction arithmetic up there, 1/2 minus 1 is minus 1/2. Yeah. And that doesn't look like our previous expression for the derivative of the square root. But again, using exponent rules, x to the minus 1/2, I can write as 1 over x to the positive 1/2. That is 1 over the square root of x. It's okay if these kinds of things make you a little bit uncomfortable. I don't know when the last time you had a math class was or what your relationship with the rules of exponents are, but the equality of those two expressions, 1/2 times x to the minus 1/2 and 1 over 2 root x, it's important that you recognize that those are two different ways of writing the same thing. So if you want to schedule an appointment with me or come to an office hour, we can talk about things like that in more detail than what I'll do in these videos. I don't want the videos to be long, but the equality of things like this, kind of recognizing that these two things say the same thing in different forms of notation, it's very important. Okay, let's move on. Let me reveal my second one here. In each one of these examples, basically, we're playing a little game. What is the power of x? Well, 1 over x itself, again, by rules of exponents, would be x to the minus 1. Yeah, the reciprocal function can be written as a power. It's the negative first power. So the power rule says that we should take -1 times x to the lower that by 1. A -1 minus 1 is -2. And again, by rules of exponents, we could write that as minus 1 over x squared. These are all coming about from the power function rule, power rule. Ooh, this one looks busy. What do we have here? The cube root of x to the 5th. So again, maybe you want to visit me or go to the Khan Academy or something. Remind yourself that the cube root of x to the 5th is the 5/3 power. Yeah, maybe I'll just write down here in general that if you take the nth root of x to the m as a power, that's the m over nth power of x. Yeah, so for differentiation purposes, you always want to treat radical functions like that, algebraic functions like that, as exponents. This side is much better for differentiation because you can use the power rule. So in particular, if that exponent is 5/3, well, the power rule says bring it down and multiply by x to the number that's 1 less than 5/3. Maybe you want to stop the video and do this at your own pace, but 5/3 minus 1, because 1 is 3/3, is 2/3. Yeah, and if you wanted to write that back in radical notation, there's really no reason to do this. I'm just trying to practice the skill on the left over there. I would write that as 5/3 times the cube root of x squared. Right, so that's the derivative of the cube root of x to the 5th. It's 5/3 times the cube root of x squared. Cool. Okay, so there's the power rule. It's going to be very important, fundamental for us. Now I want to state without proof 3 more differentiation rules. I've written the word 3 here to warn you how many are coming, but I think to squeeze all of this on one slide, I don't think I'm going to be able to keep that visible. So here they are, the constant multiple rule, the sum rule, and the difference rule. And well, what do they say? They basically give you a way of differentiating functions that are combined by either multiplying functions by a number, adding functions together, or subtracting them together by differentiating those components separately. So looking at, say, the constant multiple rule, it says that the derivative of a constant, you have this constant times f. If you want, you can just differentiate f itself and then multiply by the constant. If I wrote that in the Newtonian notation, it would say something like if you have c times f of x and you want to take the derivative of that, you can take c and multiply it by the derivative of f of x. Right? So that's the Newtonian notation of writing that same thing. The sum rule says that if you have two functions added together and you want to differentiate the result, you can differentiate each piece, each function itself, each term, and then add those together. So again, in the Newtonian notation, and I think I'm going to drop the of x here just to save a little bit of room, but I mean it, f of x plus g of x prime is, well, f of x prime plus g of x prime. Yeah, so the derivative of a sum is the sum of the derivatives, if you like that. The third one just says the same thing works for minus. If you're taking the derivative of a difference, you take the difference of the derivatives in the same order. Sorry about that. All right, so let's illustrate how you can use these rules. Maybe you want to jot them down real quick, or if you have your book open on another screen or something like that. But I'm not going to be able to keep them all visible. But let's check out how to use these things. Here I've got an example where I've taken three power functions, x to the fifth, x cubed, and x, and I've combined them with addition and subtraction. Yeah, so you don't have to write this out, but I'm gonna do it in this first example. If you want to take the derivative of that, those sum and difference rules say that, well, you can take the derivative of the x to the fifth term, add to that the derivative of the x cubed term, and subtract from that the derivative of the x term. Yeah, so we're going to call that term by term differentiation. And very quickly, you won't write that intermediate step. Very quickly, your brain will just process reading the thing left from right. You'll write, okay, well, the derivative of x to the fifth is 5x to the fourth. It's the power rule. Derivative of x cubed is 3x squared. It's the power rule. The derivative of x we wrote above is 1. All right. So again, this final form, that's why those differentiation rules are kind of nice. You can go sort of directly from here to here without writing that intermediate step. You're just looking at the terms one at a time, writing down what their derivatives are, keeping the arithmetic signs the same in between. Let's practice it. Switching the variable name, I want to try to get you used to the not all things are always called x. And this time I am going to skip this intermediate step. Okay, so I'm just looking at these three terms. Maybe before I write it, I kind of mixed something in here. I'm taking the derivative of, well, 7t to the fourth. What power of x is this 1 over t cubed? You have to manipulate that a little bit before it's ready for the power rule. You want to write that as t to the negative 3. So for the power rule, you always want things written as an exponent, no fractions. So 1 over t cubed is t to the negative 3. And now let's just differentiate term by term. All right, the first term has a constant multiple 7 in it, but that rule says leave the 7 there. So it's 7 times the derivative of t to the fourth, which is 4t cubed. Yeah. Here I've got subtract, bring the negative 3 down, lower that exponent by 1. What's the derivative of the constant pi? Pi is just a number that's approximately 3.14. The derivative of a constant is 0. Do I have enough room to simplify this a little bit? 7 times 4 is 28, t cubed. Subtracting a negative 3 is like adding it. So you get negative 3, t to the negative fourth plus 0. And again, with some practice, you'll pretty quickly be able to just go right to here from the original statement of the problem. Yeah, so you can get used to this when you bring that 4 down and it gets multiplied by the 7. You'll get used to just writing, well, it's 7 times 4, it's 28. Nice. Let's do a couple of examples where we kind of circle back and look at some notions that we discussed in the past. So in particular, I want to involve this word tangent line. So in this problem, I'm really asking a question about a derivative, but I'm doing it in the form of asking you about a tangent line. So I'm asking for all points on this graph, y equals x to the fourth minus 6x squared plus 4, where the tangent lines are horizontal. Yeah. What's a horizontal line? I mean, it's parallel to the x-axis. And what's the slope? The slope of a horizontal line is 0. Yeah. So I'm asking, what are all the points on this line where the tangent line slope is 0? Let's switch over to Desmos real quick and just kind of get a visual of what this question is asking. I always encourage, I encourage you to do this. When someone's asking you a math question, sometimes the form that you're being asked the question may be unfamiliar to you, so you can kind of switch it. So here I've got Desmos all set up. I've plotted that function, x to the fourth minus 6x squared minus 4. And now looking at this picture, it kind of makes more sense to me that, yeah, I see some places where the tangent lines are horizontal. One of those places would be down here. In fact, if I, oops, I didn't mean to do that. If I mouse over it, Desmos is even giving me a decimal approximation for the answer. Minus 1.732 comma 5 is this point. There's another place where the tangent line is horizontal. Looks like it's at 0 comma 4. There's a third place. And assuming that this graph kind of tells the whole picture, it doesn't look like there's any more. So I expect 3 answers to this question, 3 places where the tangent line is horizontal. All right, so let's switch back to the whiteboard and see if we can't calculate where those places are. But do you agree that it's good to rephrase the question? Maybe when I first posed this thing, find all values of x for which the tangent lines are horizontal, maybe it was meaningless. But then looking at that picture, I'm saying, oh yeah, where are those 3 places? Those 3 places where the function was sort of turning around. All right, so I'm just going to translate this question for us. Find all points where the tangent line. So we're looking for tangent slopes equaling 0. That's just sort of a short rephrase of the question. Tangent slopes are derivatives. Yeah, so this is the mathematician in me. I'm switching that question for an equation. This is just asking me, solve the equation y prime equals 0. Okay, well, we have to compute y prime, yeah? Y prime will compute by differentiating term by term, x to the 4th minus 6x squared plus 4. So let's do it. So the derivative of x to the 4th, well, it's 4x cubed. Derivative, and then I'm going to subtract the derivative of 6x squared. You bring the 2 down and multiply it by the 6, you get a 12. So the derivative of 6x squared is 12x. The derivative of 4 is 0. So that's the equation we need to solve. 4x cubed minus 12x plus 0 is 0. Or if we clean that up a little bit, I think I might factor out a 4x. So I've got the equation 4x times x squared minus 3 is 0. And I personally like to solve polynomial equations like this by factoring them. X squared minus 3 is the difference of 2 squares. So I'll factor it. And then in that final form, let's see if I've left myself enough room, I can see that there are 3 values of x, just like the picture told us. Because if that product is equal to 0, either x has to be 0, or x has to be the square root of 3, that's the only number that can make x minus root 3 0, or x has to be negative the square root of 3. All right, so if I write those down, x is 0, x is the square root of 3, x is negative the square root of 3. You can get out a calculator and check what the square root of 3 is as a decimal. I think that you'll see it's about minus 1.7. It's about what Desmos said it was. All right, but then we were asked the question to find points on the graph where the tangent lines are horizontal. So although in some sense this is an answer, I don't want to say, oh, x is 0, root 3, and minus root 3. Those aren't points on the graph. Yeah. To get the corresponding points on the graph, we have to plug those x values back into our original equation. Let me just sort of make myself a little copy of that equation here where I can bring it down and see it all on one screen. So if I want to know what point on the graph we're talking about, well, I have to plug these things in. So if I let x equal 0, that's the easiest one to plug in. We can see that y is 4. Yeah. 0 minus 0 plus 4 is 4. So one of the points, just like we saw on Desmos, is 0, 4. Cool. Then the arithmetic will be a little bit harder, but we have to plug in x equals the square root of 3 into this equation, right? So the square root of 3 to the 4th power, so it's root 3 times itself 4 times, that's going to be 9. And then we have to subtract root 3 squared times 6. That's 6 times 3. That's 18. And then we have to add 4 to that. Yeah? And if you take 9, well, I personally would take 9 and add 4 and get 13 and then take 18 away from it. But you can do it any way you like. You're going to get minus 5. So the point that corresponds to x equals root 3 is minus 5, just like we saw on Desmos. And then, well, this function is an even function in the sense that these exponents are both even. Even this one is x to the 0. And when you plug in the opposite of a number into an even function, you're going to get the same value. So you can do this at your own speed, but I'm going to take advantage of that and say that when I plug in negative root 3, I'm also going to get negative 5. So that's the final answer to my question. Find the 3 points where this thing's tangent lines are horizontal. It's these 3 points. Those 3 points are 0, 4, root 3, minus root 5, and negative root 3, minus root 5. And the picture that we looked at on Desmos confirms that there should be no more answers than that. All right, a couple more loose end examples here. Just again, I want to circle back and kind of use some vocabulary, practicing this new skill and circling back into old ideas. So here we've got an equation of motion of a particle moving along a line. It looks really busy, but don't be intimidated by it. This thing just tells me where I'm at on a number line at time t. Units are important, so we're measuring distance on this number line in centimeters. Time is measured in seconds. And the question is asking us for the velocity and the acceleration. So maybe this is a good place to pause the video if it's not immediate in your mind. How are those things related to S? How is the velocity V and the acceleration A computed from the position? So pause for a second and go look it up maybe, or think about it. I'm just going to continue on here and remind you that the velocity function, it's the first derivative of position. So the velocity function, I'm looking at this polynomial function up here, and I'm going to differentiate it term by term. I'm going to go kind of fast. You can slow this down. I hope you'll pause it and compute it before me, actually. But just using our sum, constant multiple, and difference rules together with the power rule, the derivative of that function s of t, let me write it, s prime is velocity. Well, it's 3 times 2, or 6, t squared. And then I should subtract 2 times 5, or that's 10 times t to the first power. The derivative of 3t is 3, and the derivative of 4 is 0. So there's my velocity function. Usually I won't write those zeros, but here are 6t squared minus 10t plus 3. And what are the units? What are the units on velocity? It's the rate of change of position with respect to time. Position is in centimeters, time is in seconds. So can you say it before me? The rate of change on velocity the units on this velocity would be centimeters per second. So that's as a function of t, how quickly this thing is moving together with the direction that it's moving. Okay, and then the acceleration. How is acceleration? Well, acceleration is the derivative of velocity, or if you prefer, the second derivative of position. So I'm looking right here at the velocity function using those power, sum, difference rules again. So the acceleration, it's 2 times 6 is 12t, minus 10 is the derivative of 10t plus 0. Derivative of 3 is 0. So the acceleration is 12t minus 10. And what are the units? Well, again, the exact same principle. It's the derivative of velocity. So its units are velocity units, centimeters per second, with respect to time, seconds. And we said before that we're going to pronounce that as centimeters per second squared, units on velocity. Cool. All right, I'm going to end this video just with one kind of homework hint. In the book problem homework, the author likes to give you functions that you can differentiate with the power rule in a slight disguise. You have to do a little bit of algebraic simplification before the power rule will apply directly. So let me give you some example. I'm just going to make this up quickly on the fly here, but maybe I want to take something like, say, x cubed minus x squared plus 11 and divide that by, I don't know, x squared, and then take its derivative. Okay, well, in this form, I can't really use the power rule because this function is not just combined power functions by adding and subtracting them. I've got this division. I'm dividing by x squared. But if we simplify that a little bit using the rules of exponents, then we can use the power rule. All right, so what do I mean by that? If I'm dividing a sum by x squared, I can divide each term in that sum by x squared. So I'm not doing any calculus here at the moment. I'm just going to redo some algebra, but I can take this x cubed and divide it by x squared, subtract x squared divided by x squared, and add 11 divided by x squared. And take the derivative of that. But still, I need to simplify this thing a little bit. Rules of exponents. X cubed over x squared is x. X squared over itself is 1. 11 over x squared, I'm going to write it as 11 times x to the negative 2. There. Now it's ready. Now it's ready for the power rule. All right, so if we take the derivative term by term, derivative of x is 1, derivative of 1 is 0. The derivative of that last term will be negative 2 times 11. That's negative 22, x to the negative 3. So if we want to rewrite that thing to make it look pretty, we could write it like this, or if you like, you could write it as 22 over x cubed. You can get a common denominator. I don't know, you can knock yourself out rewriting that thing algebraically. But that's just kind of a little homework hint that the author, in addition to changing the variable names, you're going to see every letter under the sun. The author likes to do stuff like this. The author likes to give you, it's good algebraic practice, right? So if you're looking at a homework problem in this section 3.1 and it seems like, hey, the power rule doesn't apply, you got to tell yourself, okay, well, you got to do some algebra to put it in a form where the power rule does apply. Okay, thanks for listening.